Hi, this is Dr. Holcomb. In this screencast, we're going to talk about stoichiometry, formula weights, the mole, and more. Stoichiometry is the quantitative study of chemical reactions. It's a set of tools and conventions that allow us to accurately depict how reactants and products are formed in accordance with Dalton's postulates and the law of conservation of mass. In particular, stoichiometry provides a bridge between the microscopic molecular perspective and the macroscopic perspective of everyday life. Stoichiometry is built on the concepts of atomic masses, the composition of compounds, and the law of conservation of mass. Combining these concepts with the ability to count atoms and molecules using a well-defined unit known as the mole allows us to determine and utilize the actual ratio of atoms in compounds to provide the quantitative, accurate depictions of chemical reactions. In other words, stoichiometry tells us exactly how many atoms or molecules are reacting or being formed in a reaction, and it all starts with the atomic masses of the atoms. The formula weight, or FW, is the sum of all the atomic weights for each atom in a given chemical formula. Atomic weights are the average weights across all of an element's isotopes and are found on the periodic table for each element. The units of the formula weight are given in atomic mass units, or AMU. As an example, we can easily calculate the formula weight for the ionic compound calcium chloride by adding the atomic weight for calcium and 2 times the atomic weight of chlorine to give the total weight of calcium chloride. Recall that the chemical formula for an ionic compound is the simplest whole number ratio of cations and anions present in the extended crystal lattice of an ionic substance. It is for this reason that the formula weight is usually used in the context of ionic compounds, while a different term is used for molecules which actually exist as specific atoms bonded together in discrete units rather than infinitely extended lattices of alternating ions. The term we use for the weight of molecules is molecular weight, or MW. Like the formula weight, it is the sum of the atomic weights in the atoms of a molecule, but in this case, it's the actual weight in atomic mass units of the discrete molecule itself. For example, the molecule ethane consists of 2 carbons and 6 hydrogens. A single ethane molecule weighs 2 times the weight of carbon plus 6 times the weight of hydrogen, or 30.070 AMU. In practice, the terms molecular weight and formula weight are often used interchangeably. In either case, knowing the molecular weight or the formula weight is the first step to knowing exactly how many atoms or molecules we're dealing with, and this is essential when using properly balanced chemical equations in which the numbers of atoms must be balanced. How is it that we can possibly know the number of atoms or molecules in a sample? The mole is how we know how many atoms or molecules are involved. Not the furry creature that burrows in the ground, but rather the unit of measurement, which is defined as the amount of any substance which has the same number of entities as there are in 12 grams of pure carbon-12. So the mole is a counting unit, one that chemists use, much like a baker uses the unit dozen to denote a fixed number of items. Whereas a dozen denotes 12 things, a mole denotes 6.02 times 10 to the 23rd things. This number is called Avogadro's number. The things being counted can be individual atoms or they can be molecules, depending on the context. And so as a baker might refer to 2 dozen donuts as a shorthand for the actual 24 donuts, a chemist would refer to a mole of water as a simple way to indicate that we're dealing with 6.02 times 10 to the 23rd water molecules. So, how much water is a mole of water? A mole of water is about 18.0 mils of water and weighs 18.0 grams. In other words, if you have 18.0 grams of water in a small beaker, you could say you have 6.02 times 10 to the 23rd molecules of water. Why 18.0 grams? Again, it all has to do with how we define the mole. We know that a single carbon atom of carbon 12, which is comprised of 6 protons and 6 neutrons, weighs 12.00 AMU by definition. And it has been experimentally determined that 12.000 grams of carbon 12 is 6.022 times 10 to the 23rd atoms. Therefore, we can create a new quantity, the mole, that is the amount of any substance that contains as many elementary entities, atoms, molecules, ions, electrons, photons, etc., as there are atoms in 12 grams of pure carbon 12. This new quantity also allows us to relate the mass of a sample and the number of entities in that sample as a quantity known as molar mass. The molar mass is defined as the mass of 1 mole of a substance in grams. This affords a number with the units grams per mole. Because the definition is based on the weight of an atom of carbon 12, which is the sum of the weights of protons and neutrons, this definition extends to all the elements in the periodic table, which are also comprised of protons and neutrons. So the formula weight for an element or molecule in AMU also gives the weight of a mole of that substance in grams per mole. We can therefore determine the molar mass of any element or compound in grams per mole using the atomic masses of the elements in the periodic table. Once we have the molar mass, we can use it as a conversion factor. That is because a single mole of substance is equal to a specific number of grams. Take a sample of carbon 12. 12 grams of carbon 12 equals 1 mole of carbon 12. Dividing both sides by 1 mole of carbon 12 gives us a conversion factor, which is equal to unity and is in units of grams per mole. The reciprocal relationship is also true, so we can use either form of the conversion factor as needed, that is, grams per mole or mole per gram. Let's consider an example. Suppose we have a sample of 5.23 grams of glucose, C6H12O6. How many moles of glucose do we have? How many molecules of glucose do we have? How many oxygen atoms do we have in this sample? We can use the formula, the molar mass, and Avogadro's number to calculate the answers to each of these questions. First, we'll calculate the molar mass of glucose from the molecular formula C6H12O6. The magnitude of the molecular weight in AMU is the same as the molar mass in grams per mole. So the molar mass of glucose is 180 grams per mole. We can now use the molecular weight and the molecular formula to answer these questions using dimensional analysis. Using the molecular weight in reciprocal form allows us to calculate the number of moles of glucose. The undesired units cancel out, leaving us with the desired unit of mole. To calculate the number of molecules, we take the number of moles and use Avogadro's number as a conversion factor, where we have 6.02 times 10 to the 23rd molecules in every 1 mole. the unit moles cancels out, leaving us with 1.75 times 10 to the 22 molecules of glucose. To determine the number of oxygen molecules in our sample, we take the number of molecules that we have in our sample and we multiply it by a conversion factor. In this case, the conversion factor is given by the molecular formula, which tells us that there are 6 oxygen atoms in every glucose molecule. We multiply the number of molecules then by the 6 oxygen atoms per molecule to give us 1.05 times 10 to the 23 oxygen atoms in our 5.23 gram sample of glucose. So we've already seen that the molar quantity of a given component also determines the molar quantity of the constituent parts. For instance, if we have a mole of nitrogen atoms, we can see from the periodic table that its formula weight is 14.0 AMU. Therefore, atomic nitrogen also has a molar mass of 14.0 grams per mole, and a single mole of nitrogen atoms would weigh 14.0 grams and be comprised of 6.02 times 10 to the 23rd nitrogen atoms. However, if we have a mole of nitrogen gas, which is diatomic, its formula weight is 14 times 2, or 28 AMU, and its molar mass is then 28.0 grams per mole. Because nitrogen is diatomic, we can also say that this 1 mole of nitrogen gas contains 2 moles of nitrogen atoms, or 2 times 6.02 times 10 to the 23rd atoms of nitrogen. Similarly, a mole of barium chloride contains 1 mole of barium atoms and 2 moles of chloride ions. If we dissolved the barium chloride in water, we would have 3 moles of ionic particles in solution, barium plus and 2 chloride ions, for a total of 3 times 6.02 times 10 to the 23rd particles in solution. We can use these concepts to calculate the empirical formula of compounds. Recall that the subscripts of an empirical formula gives the simplest whole number ratio for all the elements in the compound. If we know the mass percent composition of each element in the compound, we can use the molar mass as a conversion factor to determine the number of moles in a hypothetical sample of 100 grams. By relating the number of moles of each component, we can determine the simplest whole number ratio, which gives us the subscripts of the empirical formula. The mass percent composition of a particular element is simply the percent by weight of the compound that is due to that element. Again, percentage composition is the percent of the total mass of the compound that is due to a particular element. The formula for percent composition is the number of atoms of a particular element times the atomic weight of that element divided by the total weight of the compound multiplied by 100 to give percentage composition. Let's determine, for example, the percentage composition of carbon in a sample of ethane, which is C2H6. There are 2 carbons in the formula, so we multiply the formula weight of carbon by 2 to give 24.022 AMU. The molecule has a total weight of 30.070 AMU. This gives us the fraction of the molecule that is carbon, which, when multiplied by 100, gives us the percentage of the molecule, which is carbon, and that is 79.887%. If we had 100 grams of the sample, we would have 79.887 grams of carbon in our sample. Here's another example. Let's suppose that we have a chemical analysis for PABA which contains carbon, hydrogen, nitrogen, and oxygen in the percentages shown. We can use this information and the assumption that we have a 100-gram sample to calculate the empirical formula of PABA, or para-amino benzoic acid. By assuming a 100-gram sample, we can use the percentages as the mass for each element in grams. We then use the molar mass for each element to convert grams into moles for each element. The ratio of the molar quantities is proportional to the subscripts for the elements which make up the empirical formula. To get the simplest whole number ratio for the formula, we will divide all of the molar quantities by the smallest molar quantity, which in this case is 0.728 moles, the amount of nitrogen. When we do this, we get a molar ratio that is the simplest whole number ratio of moles for each element in PABA. This molar ratio serves as the subscripts for the empirical formula of para-amino benzoic acid. In many cases, the molecular formula will be different from the empirical formula. Recall, the empirical formula is the simplest whole number ratio, whereas the molecular formula is the actual number of atoms in the molecule. To find the molecular formula, we determine the multiplier of the empirical formula by finding the ratio between the actual molecular weight of the compound and the calculated empirical formula weight from the empirical formula. As an example, suppose we have experimentally determined the empirical formula for ascorbic acid. As an empirical formula, this is the simplest whole number ratio of atoms present in the compound, or moles of elements present in 1 mole of the compound. We first calculate the empirical formula weight based on the empirical formula as shown. This gives us an empirical formula weight of 88.0 AMU. Once we have the empirical formula weight, we'll need to know the actual molecular weight. This can be determined experimentally and is found to be 176 AMU for ascorbic acid. The molecular formula will be a multiple, Z, of the empirical formula. The ratio of the molecular weight to the empirical formula weight gives us the multiple Z. So the ratio of molecular formula to empirical formula is given by the multiple Z times the empirical formula divided by the empirical formula, and that is the molecular weight divided by the empirical formula weight, which is equal to the factor 2. Therefore, Z is equal to 2, and we get the molecular formula by multiplying the empirical formula and its subscripts by the factor 2. This affords the molecular formula for ascorbic acid as C6H8O6. We can check our answer by confirming that we can rewrite this formula as a simpler empirical formula by dividing the subscripts by 2 to get C3H4O3. This all works because the tools of stoichiometry provide a consistent method of accounting for all the atoms in a compound and all the atoms in a reaction. It's a core foundation of chemistry and allows us to understand and predict the outcomes of chemical reactions and many of the properties of compounds.